All right, let's do some homework problems. We're going to start by looking at number 18, 18. And number 18 says, state the domain, the vertical asymptote, and the end behavior of the function. And it's this function, negative log of 3x minus 4 plus 3. And it wants the domain, the range, and the asymptote. Wait, that's not what it said at all, is it? Domain, vertical asymptote, and end behavior. It doesn't want the range. We're going to do the range anyway, because the range of all of these, the range of any logarithmic function is all real numbers. So it didn't ask for it, but we did it anyway. The domain. We can't take the logarithm of a negative number. We showed that in the last video. It's because the domain of a logarithm is the range of an exponential function, and exponential functions are never negative unless we have function transformations. So we go off to the side and say the inside of this logarithm has to be strictly positive. So 3x has to be bigger than 4, or x has to be bigger than 4/3. How do we write that in interval notation? Parenthesis, because 4/3 is not included, so it's a bracket if it's included, parenthesis if it's not included, and it goes off to positive infinity. Range is all real numbers. The asymptote is always at the edge of the domain. Just like in exponential functions, the asymptote was always at the edge of the range. If it's at the edge of the range, it's y equals. If it's at the edge of the domain, it's x equals. It's a vertical line. The equation of a vertical line is also x equals. And the end behavior. Now you could graph this on Desmos, or you could use some function transformations, right? Normally logarithms look like this. This is a normal logarithmic function. Our logarithmic function, though, is getting reflected about the x-axis. Right? This negative right here means that ours is basically upside down. And it's getting shifted to the left, it's getting stretched and compressed, it's getting moved up 3, but for end behavior, that negative is the only thing that matters. So as x goes to positive infinity, as x goes to the right, the function goes as far down as we want. Just keeps on going down, very slowly, but it does keep going down. And as x approaches the other direction, as x approaches the end of the domain from the, like on the left side of the domain, so as x approaches 4/3 from the right, the function should go off to positive infinity. Let's check all of these answers with Desmos, though. Let's graph this on Desmos. We're going to get y equals negative log, it's the common log, 3x minus 4 plus 3. Let's look at this. All right, so we have a vertical asymptote. Where's our vertical asymptote? It is at about 1.3 something. Oh, we guessed it was at 1 1/3. Good. The domain is, yep, everything to the right of that. The range is all real numbers. As x goes to the right, it goes down as far as we want. As x goes to the left, part of the domain, it shoots off to positive infinity. We're good to go. And again, remember, you can use arrow notation like this, or you could use limit notation. The limit as x goes to positive infinity is negative infinity. And the limit as x goes to 4/3 from the right, oops, I forgot my f of x here, equals positive infinity. You could also use this for your end behavior. This is limit notation, which is used in calculus, or you can use arrow notation, which is more the standard thing for algebra. All right, that was 18. Let's do 28. 28. 28 says, oh, these ones match. So remember, like we said in the videos, if the logarithm has a big base, it's really, really flat, like E. If the logarithm has a smaller base, then it grows much more quickly, like A. And if you ever forget that, we'll just graph 2 logs. Graph what log base 2 of x looks like, and graph what log base 10 of x looks like. So this white graph is log base 10. It's much flatter. Okay. So in 28, that says, which one of these is log base 2? And you just have to figure out how small is 2. The smallest base is going to be A. The second smallest base is going to be B. We have log base 10, log base E, log base 2, log base 5, and log base 25. So log base 2 is smaller than 5, 25, 10. Natural log is log base E. Which one's bigger? Log base, is E bigger or 2 bigger? Euler's number E is about 2.718. So 2 is actually the smallest base. And that's how we solve this. 2 is the smallest base. So log base 2 of x is the one that grows the fastest. That's how we solve this problem. Which one grows the fastest? A does. A for effort. The phrase is A for effort, but effort doesn't even have an A, so it's not quite that catchy. Let's do 38. How come they're all 8s? 18, 28, 38. Kind of weird. All right. Match each function with the letter corresponding to its graph. Same idea. We have 3 logarithmic graphs. Which one is our answer? Let's use similar logic. So notice what jumps out to me, and what jumps out to me, it could be different than what jumps out to you. These all have different reflections. And some of them have different asymptotes. So right off the bat, notice that letter B, this orange one, has a different asymptote than the other ones. So that immediately tells us which one letter B is. It's the one with the different asymptote. So letter B has to be 38. Oh, we're done. Another way of doing that would be to say, let's look at this one. There's a horizontal reflection about the y-axis for letter B. And yeah, so the only one that has that reflection, right? Because logarithms usually look like this. So if we reflect it about the x-axis, part B, sorry, y-axis, part B is going to look like this. Or 38 is going to look like that, which is B. So a couple ways of finding out that 38 is letter B. Well, let's do 46. Sketch a graph of the indicated function. H of x equals -1/2 times the natural log of x plus 1. And just like that kind of messy, that messy example problem that we did in the video, anytime you have natural log, you're not going to be able to do things exactly. We're going to have to be approximating, okay? So here, let's just plot this and approximate. Or you can plug things in with a calculator and make a table. Right, if you want to make a table of x's and y's, you can do that as well. We can do both as well. Lots of things that we can do here. Probably the easiest thing is to start with the asymptote though. But let's graph it. Let's look at -1/2 times the natural log of x plus 1 minus 3. So where's that asymptote? Asymptote's at -1. Asymptote's at the edge of the domain. Asymptote is at x equals -1. Means we can only plug in numbers to the right of -1. That's our asymptote right there. And let's just kind of plug in some points. Let's look at, we can look at, there's not going to really be any nice ones. Look at 0 and then maybe 2, maybe 5, maybe 10. You only need, I'm only making you do 2 points. But the more points you plug in, the kind of better of an idea you can get. Oh, I said there's not going to be nice points when we have natural log. There will always be one nice point. All right, this one is at 0, -3. Yep, 0, -3. Going to be right here. When x is 2, let's find an approximation. When x is 2, it's about -3.549. 2, -3, about 3.5. 1, 2, 3, 4, 5. This is 5. And this is 10. What's the other point we chose? Chose 5. 5 is going to be about -3.896. Oh no, I forgot to switch to blue. So almost -4. All right. This graph is actually looking steeper than I thought it was going to. And at 10, -4.199. About 4.2 at -10. Connect all of these. It's a logarithm that's flipped upside down. And it looks like so. There we go. And that is what I'm expecting you to be able to do with a graph. For graphing one of these. All right. That's all the homework problems. Well, all the ones I'm going to do for you anyway. Or all the similar ones I'm going to do to help you. Sounds so bad. This is the end of the video. Let me know if you have questions and good luck.